to see a world in a grain of sand, and a heaven in a wildflower. Hold infinity in the palm of your hand, and eternity in an hour. This poem, Auguries of Innocence by the mystic poet William Blake, is the essence of what I will be trying to bring to you in this presentation. By the end of this presentation, you should be able to look at a grain of sand and understand how similar grains, called stardust, play a key role in forming the Earth and other planets. You should know how the flowers which make our world so beautiful have been created by the miracle of evolution. You should know that the whole, huge universe, although not infinite, was once so small it would easily have fitted into your hand. And in less than 1 hour you will see, not eternity, but the nearest thing to it, the whole 14 billion years of history. Hi, I'm Wyken Seagrave and I want to tell you a story. The story about how our universe and our world came to be as it is today. So what does this story actually cover? Well, I will need to include most of the basic facts of science. I will also cover all of human history, although we will find that humanity has only been on the Earth for a very short time, so it will not play a large part in our story. I will tell you about trends and patterns which this broad view of history shows us, and I will use them to make predictions about the future. I call this the history of the universe, but some people call it big history. So why should you listen to my story? Because it provides answers to questions which people have been asking throughout history, the same questions which everyone asks at some point in our lives. Questions such as, where am I? Where did I come from? Why am I here? In addition, the story teaches us useful lessons about history which can help us to predict the future. Everyone needs to know some science if they are to take a full part in modern life, but many people find it boring and inhuman. This story turns science into something beautiful, meaningful and relevant to our lives. It's quite a long story, so in what follows I can only give you a brief outline. If you want to know more, or if you don't have the time to listen to this story right now, you can read it at your leisure by going to my website, historyoftheuniverse.com, or you might want to download my book to your e-reader. It is available from the website or from Amazon. Let's begin at the beginning of our story, with the creation of the universe. We know that the universe was created almost 14 billion years ago, and I show this with a yellow pointer on the timeline. Most people think the universe began with a huge amount of energy released in something usually called the Big Bang. But we now know there were other events before that. It seems that the universe actually began with a very small amount of energy, although we are not sure what form this energy took. I show it here, as a yellow circle. We know when the universe was created, but not why. There are several mysteries about this story, questions which science cannot yet answer, and why this whole thing began is the biggest mystery of all. But who knows, if you were to study this subject, maybe you could find the answer to this fundamental question. It seems that the laws of physics in the newborn universe were not yet fully defined. It was as if nature were trying out different laws to find a set which could work. This made the young universe unstable. This in turn led to a sudden and dramatic increase in the size of the universe. This incredible growth is known as inflation. During this process, the density of energy in space remained constant. So, as the universe got bigger, the total quantity of energy in the universe increased. Energy was created out of nothing. This was only possible because the universe was in this unstable state. Inflation ended when the laws of physics became fixed. The universe now contained a vast amount of energy, and this was released in the phenomenon called the Big Bang. So the Big Bang was the final phase of inflation. The energy contained in space was now packaged up into tiny objects called particles which went shooting about and colliding with each other. From our human point of view, the most important of these are particles of electromagnetic radiation such as X-rays and gamma rays, heavy particles such as protons and neutrons, and light particles such as the electron shown here as a cloud. As we will see later, protons and electrons are attracted to each other, but at this time they could not join together because they were being constantly hit by the high-energy radiation filling the universe. Inflation was a period of very rapid expansion, and the universe continued to expand after the Big Bang, although its expansion gradually slowed down due to the force of gravity which tried to pull all the particles back together. And the universe is still expanding today. People often ask if the universe is expanding, what is it expanding into? Take your mind back to a time when people used to think the Earth was flat, and they used to say, the Earth is flat, so what happens when you get to the edge? Of course, now we know that the Earth is not flat. The surface of the Earth is curved. It is completely round, and there is no edge. In a similar way, the universe is also curved. Space closes back on itself. There is no edge. Now imagine a balloon colored like the Earth, and imagine blowing it up. The Earth is growing larger. If this happened, people who lived on the balloon Earth would see new land being created, and would ask where is this extra land coming from? And the answer is that it is not coming from anywhere. It is being created by the expansion of the balloon. It's a very similar situation with the universe. The universe is not expanding into anything. The universe is creating new space as it expands. As the young universe expanded, several important things happened. Each particle of radiation was stretched out over a larger space, and this caused it to lose energy. Particles such as protons and neutrons traveled slower, so they too lost energy. We say that the universe was cooling. There is a force of electrical attraction between protons and electrons, but just after the Big Bang they were moving so fast that they did not notice this force. Eventually, after expanding and cooling for about 400,000 years, the particles were going so slowly that they could feel the electrical force pulling them towards each other. The force of attraction was now strong enough to hold them together to form a single unit called an atom. The proton forms the tiny, central nucleus. The electron forms an outer, spherical shell around it. All atoms have this shape. An atom made of one proton and one electron is called hydrogen, and the central proton is called the hydrogen nucleus. In addition, there were other particles which contained two protons, and these attracted two electrons to form atoms called helium. The universe now consisted mostly of hydrogen atoms, with a small amount of helium. And, despite everything which has happened since, the universe still consists mostly of hydrogen and helium atoms. Everything else, including you and I, can be regarded as a small amount of pollution within this originally pure gas. By using powerful telescopes, astronomers have concluded that the universe is expanding faster now than it ever has before. This is a total surprise. We would expect gravity to slow the expansion down over time. So why is it speeding up? We do not know, but one popular theory is that the universe contains an invisible and unknown form of energy. Because it is invisible, it is called dark energy. If this theory is true, dark energy would account for 68% of all the energy in the universe. If you adjust an old TV set so it is not tuned to any station, you will see a pattern of white noise, like this. Where does this signal come from? It comes from the time when the first atoms were formed just after the Big Bang. Once hydrogen and helium atoms had formed, the radiation which filled the universe was free to travel uninterrupted. If we examine the radiation with telescopes, we see a more interesting pattern. This is called the cosmic microwave background radiation. Notice that it is almost the same in every direction, but not quite. This is because the young universe was slightly denser in some places than others. The difference in density is very small, but it had a profound effect. The force of gravity was strongest where the gas of atoms were densest. Here gravity pulled the atoms together into smaller and smaller clumps, until the gas was so dense and the atoms were pressed so closely together that the protons began to fuse with each other. This fusion led to the conversion of matter energy into radiation, which escaped from the gas and traveled out into space. The gas was shining, and we call this a star. These young stars did not live very long. After a short time, they ran out of protons to fuse together, and the outward flow of radiation slowed. Now gravity took over once more, making the center of the star contract, and so grow hotter than it had ever been before. The outer gas of the star swelled up because of the heat of the core, and as it traveled out, it cooled. The star became large and red. Such stars are called red giants. Meanwhile, the inner part of the star was hot enough to fuse protons and neutrons together to form totally new types of particles. The star had discovered a new source of energy. These particles would eventually form the nuclei of important new types of atoms. The main nuclei formed were carbon, nitrogen, oxygen, silicon, and iron. But red giants were unable to create nuclei heavier than iron, because fusing very heavy nuclei requires energy rather than liberating it. Finally, the star had used up even this new source of energy, and gravity took over once more. The star contracted and heated up, fusing together the particles at the center into a giant lump consisting only of neutrons, a neutron star. This released a huge amount of energy which was able to fuse particles together to make totally new groups never seen before, containing many protons and neutrons. The star then blew away all these new particles in a spectacular explosion called a supernova. Some of the particles created in a supernova were radioactive. This means that they would spontaneously break up into smaller groups, which would go shooting apart at high speed. Why did they do this? We have seen that a proton and an electron attract each other because of the force of electric attraction, while all protons repel each other because they have the same type of electrical charge. A radioactive nucleus contains many protons, too many for them to stay together inside a single particle. As the fragments fly apart, they carry energy with them, and this is what keeps the center of the Earth hot today, creating volcanoes and earthquakes. High-energy radioactive fragments can cause serious damage to living things. One interesting aspect of radioactivity is that we cannot predict when an individual nucleus will decay. It seems to be purely random. On the other hand, if we have a large number of nuclei, we can predict very accurately how long it will take for half of them to decay. This means that radioactivity is a sort of clock, and this allows us to work out the age of rocks on Earth. Nuclei of carbon, nitrogen, oxygen, silicon, and iron which had been formed during the red giant phase, and the radioactive nuclei formed during the supernova, were all thrown out of the exploding star. On the way out, they collected electrons, which turned them into atoms which had never been seen before in the history of the universe. These, together with the surrounding hydrogen atoms, are the stuff which you, and I, and the Earth are all made from. As they picked up their electrons, some of these atoms gained too few, and so the positive electric charge of their nuclei showed through to the outside. Other atoms gained too many electrons, giving them a negative charge. These opposite charges attracted, and so these atoms stuck together. The force holding these atoms together is called an ionic bond. This type of bond is very strong. It is typically found holding together the atoms in rocks and minerals on the Earth today. Around a supernova, these atoms collected into tiny specks of dust called stardust. Other atoms were able to stick to these specks of stardust, yet still move around and interact with each other. Atoms began to stick together in a new way, forming a weaker bond called a covalent bond. These groups of atoms formed the very first molecules. These are important to us because we are made of molecules. Here I show an example of a simple molecule, made of two hydrogen atoms. It is called H2, and this is what it would look like from the outside. However, It will be easier to understand the structure of molecules if we think about the bonds between the atoms rather than the outside appearance. This is what H2 would look like if we could see the covalent bond between its atoms. Notice that each hydrogen atom can form just one covalent bond. However, other atoms were able to form different numbers of covalent bonds. This is important because, without this variety, life, as we know it, would be impossible. Here are some molecules made from combining hydrogen with oxygen, nitrogen, and carbon. Notice that oxygen can form 2 covalent bonds, nitrogen can form 3, and carbon can form 4. These simple numbers are the basis for a great deal of chemistry. You can remember how many bonds each of these atoms form by memorizing the word hunk, since hydrogen, oxygen, nitrogen, and carbon atoms have respectively 1, 2, 3, and 4 covalent bonds. Water is a very special molecule, and it plays a star role in our story. It gains its special properties because of its V-shape, caused by the 2 hydrogen atoms sticking out like ears from the oxygen atom. The hydrogen atoms of one molecule are able to stick to the oxygen atom of another molecule, with a relatively weak force, shown here as a dotted line, called a hydrogen bond. It is hydrogen bonds that make water molecules hold together to form liquid water on Earth, instead of evaporating quickly. So hydrogen bonds are responsible for the world's oceans today. But they were also important early in the history of the universe. When water molecules are very cold, as they were when they stuck to stardust, their hydrogen bonds become very sticky and hold them together to form solid ice. Icy mantles formed on the outside of grains of stardust. As we will see later, this made the stardust stick together to form planets. So ice was very important in forming the Earth. Notice that there are large spaces between the water molecules in ice. This is why water expands when it freezes, and this is what makes icebergs float on the Earth today. This is a very unusual property. If ice sank when it froze, as most substances do, then all the oceans of the Earth would have frozen solid, and life, as we know it, would be impossible. When ice expands, it also breaks rocks apart on the Earth, causing mountains to erode over time. And hydrogen bonds with water are fundamental in shaping the molecules of life. Thus, in many ways, water has played a key role in the history of the universe. As the first stars were forming and exploding, so the whole structure of the universe was changing. Gravity was pulling the stars and gas and dust into filaments and threads, which eventually broke up into the groups of stars we call galaxies. Gravity has continued to shape the large-scale structure of the universe throughout history. Each dot in this computer simulation represents one galaxy. Galaxies are arranged into clusters, and the clusters form enormous walls surrounding almost empty space. The universe today contains hundreds of billions of galaxies. To put this into perspective, imagine a normal room filled with sand. For each grain of sand, there is one galaxy in the universe. We live in one of these. Each galaxy is typically millions of light years away from its neighbors, which means that, traveling at the fastest possible speed, it would take millions of years to travel from one to the next. We will therefore probably never leave our galaxy. We are trapped here, so we better make the most of what we have. What holds the stars together in a galaxy? And what holds the galaxies together in walls and clusters within the universe? Astronomical calculations show that the force of gravity created by the stars, gas, dust, and other visible matter within the galaxies is not strong enough to hold them together. The stars should go shooting off separately, but clearly they do not. This has led astronomers to speculate that there must be another form of matter, an invisible material, which holds the galaxies together. They call it dark matter. If this theory is true, then this invisible matter must account for 27% of all the energy in the universe. The visible matter, the stars, gas, and dust we can't see is only 5%. The bulk of the energy in the universe is the dark energy I mentioned earlier. We live in a galaxy called the Milky Way. It is a typical barred spiral galaxy consisting of a flat disk, in which the stars are arranged in a Catherine wheel pattern. Notice that not all galaxies are of this shape. Some are structureless clouds of stars. We do not have an image of our own galaxy from the outside because we live inside its flat disk. This is an artist's impression. We live near a star called the Sun, which is about 2/3 of the way out from the center. The Sun and its planets go all the way around the galaxy, once every 250 million years. As the Sun orbits the galaxy, it frequently passes in and out of the spiral arms. This may take it close to other stars, possibly causing problems. The Milky Way is an average spiral galaxy and contains hundreds of billions of stars, of which the Sun, our nearest star, is just one. To put this in perspective, imagine a normal room filled with sand. For each grain of sand, there is one star in the average galaxy. This is a view of Andromeda, our nearest large neighboring galaxy. This gives a better idea of the flat structure of spiral galaxies. Notice that the large bright dots in the image are stars within our own galaxy. Our galaxy, and probably all other galaxies, contain many planetary systems, such as the one we live in. New ones are being created all the time. We are now going to skip forward in time and watch how the Sun and its planets formed 4.6 billion years ago. Within the disk of a spiral galaxy, like the Milky Way, the stardust, which had been created around dying stars, gradually accumulated into dense clouds of pollution. New stars are continuously being created within these clouds. Each new star is surrounded by a cloud of gas and stardust. So how was our solar system created? Because each new star is rotating, this cloud is flung out into a flat disk. Let's watch what happens. We have seen that stardust grains were covered with ice. When stardust grains collide, their icy mantles stick together to form small lumps, like dirty snowballs. Over a few million years, these snowballs collide, the ice melts and gravity gathers the stardust into planets. The result is that planets are created in a flat disk around the star. This diagram shows the relative sizes of the Sun and its planets, but note that they are much too close together. Really, there are huge distances between them. We live on the little blue 1/3 from the Sun. The four small rocky planets near the Sun are Mercury, Venus, Earth, and Mars. Next comes a ring of tiny objects called asteroids. At some time they might have formed a planet which broke apart, or maybe they are the remains of a planet which tried and failed to form. Asteroids sometimes hit the Earth as meteorites. Next come the two gas giants Jupiter and Saturn, and then the two blue icy planets Uranus and Neptune. Far from the Sun, the Kuiper belt contains icy snowballs which never collected into planets. Sometimes they wander near to the Sun, their ices evaporate, and their long tails of gas and dust are visible to us as comets. Pluto, which was once considered as the 9th planet, is merely one of many similar objects in the Kuiper belt. We will now focus on one planet, the Earth, within the planetary system forming around the Sun, and we will begin by looking at its inner structure. Like the other planets, the young Earth became very hot as it formed and it melted. This allowed the heavy atoms to sink to the center of the planet. They were under so much pressure that they formed a solid inner core, probably made of iron and nickel. Even today, it is almost as hot as the surface of the Sun. It is kept at this high temperature by the decay of radioactive atoms within it. As we have seen, radioactive decay is as regular as clockwork, and by examining radioactive atoms and rocks on the surface, we can date the formation of the solar system to 4.6 billion years ago. The inner core creates a magnetic field around the Earth. This shields the surface of the Earth, and therefore living things, from the solar wind, from many cosmic rays, and, most importantly, from particles emitted by occasional solar flares. Without the magnetic field, strong solar flares could be lethal to life on Earth. Every 500,000 years or so, this magnetic field reverses. The last reversal occurred over 750,000 years ago, so we can expect another one in the next few thousand years. During the period of reversal, we expect that the change in field will affect our compasses, and might well expose us directly to solar flares. Above the inner core lies the outer core, also made of iron and nickel. Because it is under less pressure than the inner core, it is liquid. The outer core is kept hot by contact with the inner core. Driven by the heat of the inner core, below it, convection currents of hot rock are constantly circulating in the outer core, similar to the water in a pan on a hot stove. These convection currents in the outer core heat the layer above. The lightest rocks, made mostly of silicon and magnesium oxides, floated above the outer core to form the mantle. Heat rising from the outer core created convection currents within the mantle. As they were heated, the lightest rocks rose up through the mantle and emerged onto the surface to form giant volcanoes. These released gases which gathered around the Earth and formed the first atmosphere. The atmosphere today contains molecules of oxygen which are produced by plants and used by animals to breathe. But the early atmosphere was very different from the air we breathe today. It consisted of gases such as methane, ammonia, water vapor, and carbon dioxide, but it contained none of the oxygen molecules which keep us alive. However, it did contain water vapor, and this fell as rain, collecting in rivers, lakes, and oceans which covered most of the young Earth. As we have seen, water expands when it freezes. Freezing water was able to crack the rocks of old volcanoes. Also, the chemicals in the rain rotted the rocks. The tops of the early volcanoes gradually weathered down and their fragments were carried into the oceans. However, their roots were left still floating on top of the magma. Hot magma from the mantle continued to rise, forming long cracks beneath the oceans. It then spread out in large sheets, creating the oceanic crust. As the oceanic crust spread out, it pushed along the remnants of the early volcanoes, which stuck up out of the ocean, forming the first continental fragments. This process is still continuing today, and is called Continental Drift. Sometimes two sheets of oceanic crust collide. One of them can slide under the other. This is called subduction. Earthquakes are common as the crust sinks back into the mantle. Friction also generates heat, which melts the oceanic crust, and perhaps also the continental fragment, creating volcanoes at the edge of the continent. This is how the Andes Mountains are being formed today. Sometimes two continents collide, and new mountains are formed, such as the Alps and the Himalayas. The map of the continents has changed over time, and this has had effects upon the climate and on the evolution of life, for example, by creating new environments which living things can exploit. The Earth's climate has changed continuously over time. Here I am not talking about weather, which is the day-to-day changes, but the long-term changes over hundreds of years which we call climate. The temperature of the Earth, and therefore its climate, has changed a great deal over time. This graph, for example, shows global temperature changes over the past 450,000 years. The change in temperature has affected living things. There are various reasons why the Earth's climate changes. Partly because of differences in the amount of energy the Earth receives from the Sun. Partly because the quantity of that energy which is trapped in the atmosphere varies, depending on what gases it contains, especially the greenhouse gases such as carbon dioxide. and partly because of differences in the amount of sunlight reflected back into space by things like snow and ice. Sometimes the Earth has been very hot, and sometimes it has been very cold, perhaps even completely covered in ice. As we will see shortly, life depends on the complex interaction of two different sorts of molecules. Scientists have performed experiments which add energy to the simple molecules found in the young Earth's atmosphere. This energy could have come from lightning or from sunlight or from the magma beneath the oceans. The results of these experiments show that both of these main constituents of life could have been created on the young Earth. But it is very difficult to imagine how these molecules might have begun to interact to form life. This is one of the greatest mysteries of this story, and scientists are currently searching for clues by visiting other planets, by examining early rocks, and by searching for signals from intelligent life elsewhere in the universe to try to solve this mystery. Does life exist elsewhere? If it turns out, as is perfectly possible, that life only exists on Earth, then that makes this planet perhaps the most precious object in the universe. If this is the case, we have even more reason to look after it with the utmost care. Life today is a complex system which involves the interaction of two types of molecules, amino acids and bases. In living things, bases are arranged in long chains called nucleic acids. As we will see, the order of the bases in a nucleic acid is very important. Because of their shape, bases are able to join together in pairs, so producing two complementary chains. This is the well-known DNA. In life today, amino acids are arranged in long chains called protein. Proteins are pulled into a specific shape because of the hydrogen bonds they form with the water around them. This shape allows every protein to do a useful job. They are the worker molecules, for example building other molecules, or breaking down food into its component parts. In life today there are proteins which can separate the two halves of DNA, and build new DNA on each half. Each of these DNA molecules is an identical copy of the other. This allows living things to reproduce. The process of life relies on a complex object called a ribosome, which is made of both nucleic acid and protein. The ribosome has the ability to assemble amino acids into proteins using the information encoded by the sequence of bases in nucleic acid. By using different nucleic acids at different times, a living thing can make just the proteins it needs at the time it needs them. Reproduction of DNA is not perfect. Sometimes mistakes occur. More often, DNA is damaged by accidents, such as the presence of radioactive atoms. This is called a mutation. Changed DNA produces a changed protein. Normally this is of no use, and the living thing which has it will fail. But very occasionally the new protein is useful, and the thing which possesses it will reproduce faster than other living things. Over millions of years, several lucky accidents like this can produce a totally new type of living thing. This process is called evolution. Evolution led to living things becoming packaged up inside oily membranes to make the first cells. We call these simple cells bacteria. One of them is called a bacterium. The oldest bacteria found so far lived about 3.5 billion years ago. Early bacteria lived on the chemicals they found on the young Earth. However, some bacteria evolved the ability to capture the energy of sunlight in a process called photosynthesis and used it to create their own food. These bacteria were able to grow much faster, and life began to spread across the Earth. As a consequence of photosynthesis, a dangerous new gas called oxygen was released. This was poisonous for most of the bacteriolae then, and most of them died. This was the first example of a mass extinction of species. However, some bacteria were able to make the oxygen safe by a process called respiration. This also gave these cells a new source of energy. Cells which could not respire began to live close to those cells which could, and both cells gained from this arrangement. Soon the respiring cells took up residence inside these host cells, creating a totally new type of cell called a eukaryote. The name means good nucleus and is given because these new, large cells had their nucleic acids packaged into the nucleus at the center of the cell. Eukaryotes evolved gradually over the next 1.5 billion years, until, about 500 million years ago, they began to live together in colonies. Each cell in a colony took on a specialized role. Sponges were among the earliest such animals. Notice that they appeared relatively recently in Earth's long history. Animals now began to evolve rapidly. Forms appeared which now seem very strange to us, such as this reconstruction of Kimberella, which appears to have lived by eating bacteria on the seabed. Many of these early types of animals have since died out, but others survived, including all of the major groups we see around us today, such as worms, insects, slugs, spiders, and animals with backbones. But one thing all these early plants and animals had in common was that they were only able to live underwater. Within about 50 million years, first plants and then animals evolved to live on land, but the earliest ones were still obliged to return to the water in order to reproduce, such as this dragonfly. Reproduction is one of the most complex parts of the life of any living thing, and so it is no surprise that evolution of their reproductive systems lagged behind the other changes which made life in air possible. However, about 300 million years ago, plants managed to solve the problem of how to reproduce on land by creating seeds. Soon afterwards, animals also began reproducing on land by laying eggs, similar to this turtle. Several mass extinctions of life have occurred throughout history, but the greatest of them all happened about 250 million years ago, marking the boundary between the Permian and Triassic periods. 96% of all marine species disappeared, and vast numbers of animals and plants vanished from the land. One theory is that this was caused by a huge meteorite colliding with the Earth. The resulting debris was thrown up into the atmosphere, shutting out the sun, and causing plants to die and animals to starve. Following the mass extinction, dinosaurs were able to rapidly evolve and fill all the ecological niches left vacant by the dead species. The earliest mammals also appeared at this time. Ironically, as we will see, the dinosaurs were also destined to be wiped out by another meteorite. About 200 million years ago, new types of reproduction appeared in the plants, invertebrates, and vertebrates. The plants evolved flowers which attracted insects and other pollinators, so helping them to spread much more efficiently. Insects such as bees and ants evolved into social colonies, which meant that individual animals were able to specialize to perform particular roles within the colony. At about the same time, the early mammals evolved a way of retaining their young inside their mothers' bodies rather than laying eggs, which allowed them to develop in more complex ways, and their reptilian ancestors. About 65 million years ago, another meteorite wiped out the dinosaurs, leaving the land and sea clear for mammals to diversify rapidly into these vacant niches. Our ancestors, the early primates, evolved from an insectivore about 50 million years ago. An ice age began about 30 million years ago, probably caused because Antarctica drifted over the South Pole and India collided with Asia to create the Himalayas. This is the environment within which humans evolved. Small intelligent apes, called Homo habilis, appeared in southern Africa about 3 million years ago. They were able to walk on their back legs, and their front legs evolved into hands. They were able to make and use tools. They also learned how to speak, and so they could pass on culture and learning from one generation to another. They began to use fire about 700,000 years ago, and by cooking food they could access new forms of nourishment as well as keeping warm and protecting themselves from wild animals. Modern humans seem to have evolved in Africa about 100,000 years ago, and spread across the world about 35,000 years ago during a warm period in the Ice Age. The past 12,000 years of human history has been dominated by climate change. Here we show a graph of how the global temperature changed during that time. We abbreviate 1,000 years ago to K, Y, where K means kilo. At the beginning of this period, ice still covered much of the Earth. Then, about 11,000 years ago, a warm period called an interglacial began. Much of the ice melted, except on the high mountains and at the poles. As the climate warmed, some people learned how to plant wheat and other crops, while some lived as nomads, herding sheep and other animals. There were many conflicts between the nomads and farmers. From about 8 to 5,000 years ago, the interglacial reached its hottest, plants grew rapidly, and the first cities were settled. In a way, a city resembles an insect colony. Individuals specialize in a certain role, and this is far more efficient than everybody trying to do everything for themselves. Every city formed a separate state, ruled over by a king, who claimed complete power over his land and people. Cities led to trade, to the invention of writing, to the establishment of kings and priests, soldiers, and teachers. About 5,000 years ago the warm period ended, and the climate began to cool, and it continued to cool until 150 years ago. This cooling of the climate led to mass migrations of people, invasions, and wars. Then, 150 years ago, the climate began to warm rapidly, as a result of people burning coal and oil. This too is leading to mass movements of people, starvation, and wars. The Earth today faces many difficult problems, the greatest of which is the instability of the climate. Even if we could reverse the warming due to our own activities, the climate would not be stable. The long-term cooling would probably continue, leading to another glacial period. So how do we tackle global problems? We do not have a good system for governing the Earth today. Humanity is divided into 200 individual nation-states, each of which claims sovereignty over their people and their armed forces. There is no system of global governance, and the governments of many nations are not democratic. Without an effective form of global governance, wars and mass migrations will continue. This requires us all to recognize that we are primarily citizens of the Earth, and that we must give some of our national sovereignty to a global power. National governments will not accept global governance for a long time, and after many more wars. Ultimately, the people of Earth will recognize that global governance is necessary, and real peace will finally arrive on Earth. Mankind will spread to other planets, but he is not well designed for this task. Computers, on the other hand, are ideal for exploring and colonizing hostile environments, and they will gradually spread to other planetary systems. The oceans will probably evaporate during the next billion years, because the sun, like most stars, is gradually getting brighter as it gets older. 4 billion years from now, the sun will run out of fuel and become a red giant. This will destroy the Earth and most of the other planets. But by then computers will have spread far out into the Milky Way Galaxy. They might even have reached other galaxies nearby. We are not sure whether the universe will continue to expand forever, or whether it will begin to contract, perhaps eventually forming another Big Bang. If you have enjoyed the story, then you might like to find out about some of the fascinating details. If so, there is an electronic book you might like. History of the Universe by Wyken Seagrave contains over 300 images and costs less than $3. You can find it at the webpage howtobook.co.uk or from any Amazon website. You can also find a lot more information by visiting my website historyoftheuniverse.com. Once you have learned about where you came from, you might like to have a bit of fun and earn a free Citizen of the Universe badge, which tells you your grade of knowledge and which you can use on your own email and websites. Visit citizenoftheuniverse.org. And, if you think this story is important, you might be interested in joining a group of other people who are trying to make the story more well known. Visit bighistory.org.uk. Thank you very much for watching this presentation, and I hope you have found it entertaining and informative.